All right, we'll continue here. On my ECC, I'm going to post your grades on Gradebook. And so you can check your scores there and make sure everything's inputted correctly. There's something else you should check frequently, and that is Piazza. And so this was the discussion board I was talking about earlier, but it's pretty easy to get started. You can either click on the link that I sent out. If you didn't get that link, then you just go here. Students get started. And then you'll search El Camino. It pops up here. And then just input your class. This class is Chem. Turns out there's only one Chem class on Piazza. This is mine here, so just click that. And then you'll need a class access code. This is on the syllabus, in case you forget. But the class access code is just Chem 1B, all lowercase, no spaces. Chem 1B, that, and they'll join as a student here. And that's pretty much it. I mean, when you hit continue, it'll ask for your email. It can send you a little alert and something useful. Or what are you going to find on Piazza? I posted some stuff already here. Today's handouts, and the syllabus, and that course info sheet. Let's take a look at the syllabus. I made a mistake on the syllabus. If you look at page 2, you have 2 March 23rds and 2 March 24th. And so this wasn't supposed to be March 23rd. This is supposed to be March 30th and March 31st. And so can you cross out the 23 and 24 and replace it with 30, 31? Let's do it. You can also find the homework here. I had a question earlier. What's the homework? Well, this is the homework. So chapter 24, part 1, chapter 15, chapter 16. Chapter 16, this is the chapter somebody told me there's 63 problems here. That's a lot of problems. So how can you do? If you spend 1 hour on 63 hours, it's impossible, right? Impossible to do. And so you just got to make use, the best use of your time. This is an important chapter. Chapter 15 and chapter 16 are important, and chapter 16 especially because chapter 15 just talks about these kind of equilibrium reactions in general, gas phase, liquid, aqueous. Chapter 16 starts to focus just on aqueous equilibrium, that stoichiometry I was talking about, the Chem 1B. And so chapter 16 is really the kind of the building, the stepping stone, because if you struggle in 16, then forget understanding 17 and 18. Chapter 16 is called Acid Bases Part 1. Chapter 17 is Acid Bases Part 2. There's so much to talk about. They split out into 2 chapters. And so you got to make sure you understand this stuff in 16 before progressing on to 17 and 18. It's a stepping stone. 19, 14, 20, 24 part 2, and 25. So the entire semester is worth of homework. Oh, actually, let me take that back. Not the entire semester. There's one homework assignment missing from this. And that homework assignment's up here. It's called Chemical Reactions Practice, right here. Click on this. This thing's going to be worth 10 points, so 20 reactions here, so each one's worth half a point. Unfortunately, you don't have the solution guide for this one. But this one's not going to be due until later. You'll have more time. It's not due next week. So just a series of reactions. Some of the stuff you'll need to do that here, to do those reactions down here. Oops. This is an acid-base and redox chart. Acid-base chart here, redox chart here. One more thing, we don't have lab for a while. This is Chem 1A, 1B lab notebook. And so this is a handout I give. I didn't give this out last semester. And, normally I give this out in 1A, but I tried to cut some stuff out of 1A, so I didn't. And so I made the lab notebook, not very formal, but in 1B, the lab notebook's formal. It's just a comp notebook, but I expect you to follow or adhere to these guidelines. And I'll be checking your lab notebook periodically through the semester. So read through this here. What's the purpose of lab notebook? The purpose of lab notebook is just someplace to have a permanent record of your observations from the experiment. There's some recent experimental work handout there you can take a look at. So this is Piazza. Let's see if this has been updated. Oh, I just posted something earlier today. That's weird. It's not there. But I was asked about the recordings. I'm going to record all the lectures, and then I'll post a link here. And I just posted the one for this morning, but it hasn't shown up here yet. So maybe there's some delay in that. I'll have to double check that. But you can find that. Not only that, you can use this to ask questions. Let's say a question pops up, and post it here. And anybody's free to answer it. So if you know the answer, go ahead and write it in. Because it might take me some time to get to it. But eventually I'll get to it. So. Oh, there's one other handout here. It's chemical risk. Yeah. You know, I was looking at kids' shoes the other day. Actually, yesterday. I was looking at kids' shoes on Amazon. And so I was reading the description about the kids' shoes, and then I see the Prop 65 warning. You know the Prop 65 warning?
Cancer.
Yeah, this product contains materials known to the state of California to cause cancer. And so I'm thinking, should I buy the kids' shoes or not? You know, I don't want to buy something and cause the kid cancer, right? Kids cancer. And so, you know, the Prop 65, I was thinking about Prop 65 warnings, it's gotten too much. You know, they put it on everything, so you don't know what's risky and what's not risky. You know. And so here's a handout. It's a little bit old, but this is published by the American Chemical Society talking about exposure and risk. And so to better educate yourself, you can look at this rather than, you know, blindly following some Prop 65 warning. You know, some of them are good, like if they're spreading chromium and lead over, then you want to watch out for sure. But others, you're thinking, oh, it's too much. All right, so this is Piazza. And on Piazza, you're going to find some PowerPoints here. And so this is a review. I'm just going to cover these using PowerPoints. This is chemical reactions review. I broke it up into 3 parts, part 1, part 2, part 3. We're going to cover part 1 today, and 2 and 3 tomorrow. So let's take a look. You can just go ahead and save these. Download them. So why do I want to review chemical reactions? One of the reasons I want to review chemical reactions is because, you know, all of you are probably pretty familiar with physical properties. Can you name some physical properties for me? Color, density, mass. Maybe I should review physical properties. Insert physical properties, part 1 here. Is that it? There's got to be more. Isn't there more?
No.
Color, mass,
Smell.
smell, okay. Shape, to be physical property.
Texture.
Texture, yeah. Physical property.
What taste do you want? What taste do you want?
Taste, yeah, that could be one. Taste. Melting point, right? Boiling point, those types of things would be physical properties as well. And so, yeah, most people can name a list of physical properties, and there are lots of different ones, right? You know, how many physical properties are there? Is there a fixed number? No, there are lots. There are 2 different types of physical properties. We have the extensive properties and the intensive properties. What's the difference between the extensive physical properties and the intensive physical properties? Or tell me, give me an example of an extensive physical property. Or give me an example of an intensive physical property. Melting point would be an example of an intensive physical property. That's good. Temperature, yeah. Intensive. Well, it could be tricky. That one could be tricky, though. Depends on the thermometer. You know, because the thermometer can absorb heat, and therefore, if you measure the temperature of the ocean versus measuring the temperature of a drop of water, and the thermometer is a cold thermometer, then the thermometer is going to have no impact on the temperature of the ocean, but the thermometer on a drop of water could have an impact, could change the temperature of the drop. Put a hot thermometer on a cold drop of water, or cold thermometer on a warm drop of water, it's going to change the temperature. And so potentially it could be intensive. But the difference is intensive are independent of the amount, extensive depend on the amount. And so mass is an extensive property, energy is an extensive property. Right? Those depend on the amount. Well, what do chemists study? Chemists study this. I like definition number 2, composition, structure, properties, and reactions of substances or matter. But I don't like this. I'd change this definition. You know, I'd say the composition, structure, physical properties, and chemical properties of a substance, or just make it simple. The composition, structure, and properties. There are 2 types of properties. There are physical properties and chemical properties, and then subcategories amongst them. Well, what is a chemical property? List some chemical properties out. You know, like name some. Reactivity is a chemical property. Okay, that's correct. Reactivity is a chemical property. What else is a chemical property?
Burning.
Burning. Yeah. Burning, if you think about burning and reactivity are the same, you know. And so basically it's just chemical reactivity, in other words, chemical reactions. And burning is a chemical reaction. And so when we think about chemical properties, we think of chemical reactions. Now let me ask you the same question. How many chemical reactions are there? There are lots of physical properties, right? But how many chemical properties are there? Lots? Two? Two chemical properties? What would the two chemical properties be? Endothermic and exothermic? Okay, that's fine. We have endothermic and exothermic, and so we'll classify all the as endothermic or exothermic. But you know what common characteristic do all endothermic reactions share? Well, they absorb heat or energy from the surroundings, right? And that's it. And so when we think about this, there are different ways to classify it, and endothermic and exothermic are fine. There are other ways, but in Chem 1A, how many types of chemical reactions did Petrucci come up with? Do you guys recall? Was there a fixed number? More than two? Because, for example, combustion, that's one. Combustion happens to be an exothermic reaction. What else was there? Yeah, redox and acid base. And what else? So how many types of chemical reactions did Petrucci come up with, and did you learn? Well, a lot of people say, yeah, there are lots of different types. It's not worth learning every single type. Do you know every single physical property there is out there? Probably not. And what is the fixed number? Well, it depends on the substance you're looking at, right? It's probably not worth looking into much more than that. You know a bunch of physical properties, that's enough. But as far as chemical properties go, well, I know a bunch of chemical properties, you know, combustion, acid base, whatever. There are probably a lot more, right? And so it depends on who you took for Chem 1A. You know, different instructors do things differently. They might categorize things differently. And the reason I'm doing this chem reactions review is because not everybody is familiar with this, because it's not in the book. I categorize things a little differently than Petrucci. In fact, just take a quick survey. How many different types of chemical reactions do you expect? I mean, if you think about the number of chemical reactions that occur in nature, it's huge. You know, just think about all the reactions occurring in your body right now. Those are all chemical reactions. How many are there? Lots. Right? And so just a quick survey of what you think, or what you recall. You know, recall Petrucci saying, you know, as far as categories of reaction or types, or just a guess. And if you don't know, that's fine too. Just say you don't know. Jasmine, 3 types. Okay. Saba, 3. Eleni, 3. Brandon. Okay, that's fine. Alexandra, 3. Ashley, 5. Miral, sorry, 3. Jeffrey, 3. Wen Zui, 3. Or sorry, Vincent. I got that right. 3. Vincent D. Vincent G. A lot. Yeah, you'd expect a lot, basically. Sahab?
Okay, I feel like this is a trick question, so I'm gonna go with like one or infinite.
One or infinite?
Yeah.
Okay. All right. Okay. It's fine. You'd think there'd be infinite, new reactions appearing all the time, right? And there are new reactions. People are trying to devise new synthesis, new reactions all the time. And so, in a way, it's a trick question because, is it really a new reaction, or is that reaction similar to previously seen reactions and can be categorized as one that's similar versus a truly new reaction? Okay. For example, combustion. Okay, I burn, let's say, methane, and then I burn paper. Is that really a distinctly new reaction, or is it still just a combustion reaction? And so you could argue it either way. So it is a trick question in that. David?
I still think it's
2. Okay. Endothermic and exothermic still. Samuel? 3. Matthew? Okay. Tesla? 3. Sung? Denny, sorry. 3. It'll take me some time to get this. Taylor? Felipe? This was absent, that's right. Patrick? Okay, that's fine. Samantha? Okay, Misbah? 3. Jonathan? 5. Andrew? Andrea? 7. V? 3. Dewey? TJ? Marina? Daniel? Hannah?
Do you want me to learn last semester or just
What you learned last semester?
maybe 5?
5? Okay. Who did I miss? How many?
There's about 5 we went over last time.
5? Okay. Who else did I miss?
5.
5? All right. Yeah, one thing I learned also when I was studying, I'd like to study from the book when I transferred to UCLA, but I quickly found that wasn't very effective. I studied from the book, but primarily I studied from the notes. I studied from what the professor thought was important. And so if the professor said 5 reactions, then I'd say 5 reactions. I want to do well in the class, right? But I'm going to say there are 3 basic types of reactions, so I'd like you to agree with that. You could argue otherwise. You could say there are 5, you could say there are 7, but I'd like to hear arguments for that. And so I'll tell you why I argue that there are 3 types of reactions. And look at these here. All right, so the first few slides, actually, this was originally made for Chem 1A, so I went through properties in a lot more detail. For you Chem 1B students, this is kind of a review. So we got physical properties, chemical properties. But, ultimately, this is what I did at UCLA, at UCSB. Ultimately, what we want to do is we want to understand the properties of matter. And what are the properties of matter? Well, the physical properties and the chemical properties. We know that the physical properties are melting point, boiling point. We also want to understand the chemical properties of matter. And the chemical properties of matter, where do we get insight into that? Well, basically the properties we want to correlate with the composition and the structure of matter. When we correlate this composition, structure, and properties, we use a mix of approaches. Our most common approach is a mix of theory and descriptive chemistry. Theory is just, the theoretical foundation or basis of chemistry. Do you know what the theory of chemistry is? The theory underlying chemistry is? You know what a theory is. Actually, maybe I should take a step back. What is a theory? It's not necessarily a truth or known truth. I mean, theories can prove to be wrong. Like Bohr. The Bohr theory was proven to be wrong and abandoned and modified. Yeah, that's good. That's a pretty good definition. What is a hypothesis? Yeah. Well, basically, a theory is like a fundamental description of the underlying whatever you're studying. So in this case, it would be a fundamental description of chemistry. A fundamental description of chemistry tells us how things behave, both physically and chemically. And so we'll use that theory, and the theory that underlies chemistry is called what? What is the theory that we've been using to try to understand chemistry to this point? Not the Bohr theory, because the Bohr theory was abandoned. Not Vesper. Heisenberg is part of it. Heisenberg, it's not called the Heisenberg theory. Heisenberg was an important contributor to the theory. It's a scientific model. It is a model. What is the model? Quantum mechanics. And so we use a mix of that and descriptive chemistry. Now, what is descriptive chemistry? Descriptive chemistry is memorization, fact memorization. And so you have to do some memorization in this class. You can't do everything theoretically. A lot of people say, I don't need to memorize anything because you could just figure it out using theory. Well, you can't figure it out, everything using theory. And so there are some facts, or maybe it's just impractical. So let's give an example here. Is HCl a gas, liquid, or solid at room temperature? And so a lot of people say, I don't want to memorize HCl as a gas at room temperature. I'd rather just use theory. That way I don't have to memorize anything. And so how would you use theory to prove that HCl is a gas at room temperature? Well, you'd have to use some physics and some math and do some calculations to determine that HCl is indeed a gas. But how many hours of theoretical analysis do you have to do just to figure out something so simple? Right? And so in that case, here you just memorize. HCl is normally a gas. You can dissolve it in water to form hydrochloric acid. And so there's a lot of stuff, to have a firm, solid foundation in chemistry that you just have to memorize. That's just common knowledge. A lot of this experimental fact, this memorization stuff, you can find in books, so you don't have to memorize everything, but you can look it up as well. But a lot of this is compiled into tables, and these tables are the properties of this substance, or the properties of that substance. This lists some physical properties and chemical properties, and we use these properties often to identify substances. So, for example, if somebody gave you a beaker of clear, colorless liquid, which we'd call CCl, and said, oh, here's some water, you're thirsty, go ahead and drink it. Would you drink it? No, you'd probably want to make sure it's water first. Well, how would you make sure it's water? Well, will it mix with other water? Actually, it will. And so if I take this clear, colorless liquid and mix it with water, it mixes. Now, would you drink it? No.
No, obviously not, because lots of things will mix with water, right? Including carcinogenic and Prop 65 type stuff. And so obviously we'll want to test it. And traditionally the way you test it is you look, water has a fixed set of properties, a known set of properties. It boils at 100 degrees C. And so you test the boiling point. Well, this boils close to 100. Let's say this boiled at 98. Close enough, right? Would you drink it? Well, it could be the thermometer's off. These mass-produced thermometers could be off a degree or two. Would you drink it? No, you probably wouldn't, because there are other things that boil close to 100 too. And so you test more properties, both physical and chemical properties, to identify the substance. And so some of this, stuff we know. The liquid is clear and colorless. Well, it could be lots of different things. The substance is a gas, it could be lots of different things. But if the substance is green, yellow, corrosive gas with a boiling point of such and such, then there aren't that many green, yellow, corrosive gases, are there? What would you guess this is? Green, yellow gas.
Mustard gas?
A green, yellow, corrosive gas.
Mustard gas?
Mustard. A green, yellow, corrosive gas that you'd encounter in this lab. We aren't going to encounter mustard gas in this lab. But a green, yellow gas that we might see in this lab would be like chlorine gas, right? Chlorine, this could be chlorine gas, it could be other things, etc. And so this reminds me of a thing, to have a firm foundation in chemistry, we need some factual knowledge memorized. There was a collision. When I was a student at UCSB, a tanker truck collided on the freeway, releasing or spilling a whole bunch of acid. And there were brown, orange plumes of gas coming off the acid. And so I was watching the news, and the news person said that, there was a hydrochloric acid spill on the freeway, shutting it down. But I was thinking, no way, that cannot be hydrochloric acid, because does hydrochloric acid give brown plumes? No, it's probably, what might give brown plumes of gas? It's probably nitric acid. I was thinking that's got to be nitric acid or something else. Definitely not hydrochloric. And so we want some factual knowledge memorized. And then we try to sort things out. So if you're thinking about the chemical properties, for example, what are the chemical properties of HCl? You might think, there's so many. There's so many chemical properties of HCl. What will HCl react with? Will HCl react with sodium hydroxide? Potassium hydroxide? Lithium hydroxide? Calcium hydroxide? Iron 3 hydroxide? On and on and on. Will HCl react with magnesium metal? Will it react with iron metal? Will it react with copper oxide? And so if we're thinking about it, we don't want, if there are 5 types of reactions, what types does HCl participate in? If there are 7 types of reactions, what 7 types of reactions does HCl participate in? Any of them, or one of them? None of them? Okay, acid-base for sure. HCl is a strong acid, but is that the only chemical property? No, what else can HCl do? It can do redox, right? It can attack metals, certain metals. What else can it do? Is that it? And so the reason I have it broken down into 3 is, if we have 3 types of reactions, then we look at it in terms of those 3 types of reactions. What are the 3 types of reactions that I have? The 3 types of reactions are something I call metathesis. Metathesis are like double replacement reactions. And so in the metathesis reactions, HCl can do things like form gases like CO2, reacting with calcium carbonate. It could precipitate out things like silver, lead, mercury, etc. And so there's certain ions that HCl reacts with. Metathesis are also known as ion combinations. So we look for other ions that H plus likes and other ions that chloride likes. Fortunately, chloride only likes a few. Then we have acid-base. So it reacts with a whole bunch of bases. H plus is a pretty good Bronsted acid. In fact, we call it strong acid. Chloride is an exceptionally weak Bronsted acid. But we also have another type of acid-base reaction called Lewis acid-base reaction. And it turns out chloride is a bit more reactive than those. And then we look at redox reactions. HCl is a moderate, what we call a moderate oxidizer. And so we look. So these are some of the reactions from Petrucci. Combination, decomposition, acid-base, single replacement, double replacement, combustion. So far that's 1, 2, 3, 6 and more. And so there are a lot, and it seemed like the list didn't end. Not only that, there are subcategories of combinations. Did you guys, in Chem 4, you might have had to memorize element plus element combination, element plus compound combination, compound plus compound combination. Did you have to memorize all the variations of combination reactions in Chem 4? Maybe. The problem with that list is it's not comprehensive. So, for example, how would you categorize this reaction? This is a very famous reaction, HCl plus HNO3 plus gold. Have you seen this reaction before? This is a very famous reaction because this reaction is capable of dissolving solid gold. And the combination of HCl and HNO3 is called aqua regia. Aqua regia stands for royal water. So what kind of reaction is that? Is that a combination reaction? Is it a double replacement, single replacement? What is that? And so what it turns out it's a redox followed by a Lewis acid-base reaction. And that's how this one works. Sometimes the combinations are confusing if you don't memorize the categories. This is an element plus element combination. An element plus element combination is a redox. Whereas a compound plus compound combination is not a redox, it's actually an acid-base. This one's not a double replacement. This is a little different than a double replacement. So the reason I picked 3 types of chemical reactions is because there are 3 driving forces in nature. So all metathesis reactions have the same driving force. Acid-base, they have the same driving force, which could be different than metathesis. Redox, totally different driving force than either acid-base or metathesis. And so the reason I do this is because there are 3 driving forces typically found for chemical reactions in nature, and therefore there are 3 types. If we go back to those combination reactions, on the previous slide, these 2 combination reactions have totally different driving forces. The driving force is what drives the reaction forward. And so these are not the same driving force. Therefore, they shouldn't be in the same category, right? If they have a totally different driving force, then why would you call both of them the same combination reactions? Does that make sense? Not to me. Driving force is important. When we think about driving force, in theory, what is a driving force? It's the formation of more thermodynamically stable products from less stable reactants. And so we're going from something that's unstable to something that's stable. That's going to drive the reaction forward. And so what types of things do you look for in stability? What makes something stable? What do you think? Compound A versus compound B. Compound A is more stable than compound B. Therefore, what can you conclude about compound A versus compound B? If something's more stable, it's resistant to change. And if it's resistant to change, that tells us that the bonds are stronger. The more stronger the bonds, the more stable the compounds. And resistant to change, it would be more resistant to change. And so things that have strong bonds are stable. Things that have weak bonds are unstable. Well, do we analyze the bonds of each compound? No, we typically don't do that. We look for other cues that something's more stable. Let me skip this slide here. Skip that slide. Well, actually, let me not skip this slide. What types of things tell us that something's more stable? Like precipitation. If something precipitates, you're taking an ion from here, they come together, they're precipitating out of solution. They're forming a strong bond and precipitating. So you look for things like precipitation. But precipitation doesn't work for everything. For example, it doesn't work for all combination reactions. And so you have to look. Well, precipitation is a driving force for metathesis reactions. Whereas precipitation would not be a driving force for redox reaction. And so once we get the categories down, then we look at the driving forces individually. But that would be an example of descriptive thing to look for. There are others which we'll talk about. Here, we're just comparing. Metathesis would be double replacement or ion combinations. Acid-base, we have different kinds. Here, redox, we have single replacement, combustion, etc. I put that in this little pyramid here. So, metathesis, ion combinations, or double replacement, etc. It doesn't have to fit this pattern. You could have alternate patterns, but all the reactions were the same. You're looking for ions that like to bond to each other. And there are certain ways, there are certain clues as to what likes what. Acid-base, we have three types of acid-base reactions. Bronsted, Lowry, and Lewis are the two that we're going to focus on. Arrhenius are very simple. Redox, redox, we have single replacement, skeleton redox, redox chart, combustion, etc. And so what we want to do is we want to get an idea of chemical properties by making certain predictions about reactivity. And so in order to make some predictions, we have to make sure we always start from the same place. And we're going to have some basic assumptions here. The concentration should be approximately 1 molar, and gases should be at approximately 1 atmosphere. If the concentrations deviate significantly, then our prediction might not come out. Our prediction still might not come out because we might be missing a side reaction or something else, or a competing reaction. But still, having these predictions gives us a pretty decent idea of what's going to happen. And so, let's say, when we mix HCl hydrochloric acid with AgNO3. AgNO3 is what? Silver nitrate. Mix hydrochloric acid with silver nitrate. We expect to precipitate out silver chloride and form nitric acid. Nitric acid won't precipitate out. And this is a double replacement reaction. The driving force of this is precipitation of silver chloride. Silver chloride forms an insoluble solid. Do you guys have the solubility rules memorized? You need to start rememorizing those. But if we have very dilute concentrations, nothing happens. No precipitate forms. And so if we're at very low concentration of HCl, very low concentration of silver nitrate, it looks like no reaction occurred. But we predicted a reaction should occur. And that's just because we're too dilute. I mean, you need 1 milligram of precipitate to see it visually. Let's look at the reverse reaction here. Silver chloride and nitric, there should be no driving force for this because this is a reverse reaction of that. And so if it's favorable in one direction, it should be unfavorable in the reverse direction. And so here, silver chloride plus nitric acid should yield no reaction, NR. Because what we form here is we should form silver, what do we form? Silver nitrate. Is silver nitrate going to precipitate? No, because you know that nitrates are all soluble, aqueous. So silver nitrate's not going to precipitate, and we're going to form hydrochloric acid. And so the driving forces for metathesis are precipitation, 1, gas formation, 2. And so hydrochloric acid is not really gas formation because even though hydrogen chloride is gas, it's so soluble in water, it pretty much stays mostly dissolved in the water. And the third one is going from a stronger to weaker acid. And so nitric acid versus hydrochloric acid, do you know which one's stronger in water? Hydrochloric is stronger than nitric? Nitric is stronger than hydrochloric?
Is it HCl one of the top 7?
HCl and HNO3 are both in the top 7.
So they're saying.
They're the same. What was that effect called again? Jasmine, you recall the name of that? HCl and HNO3 are going to be the same strength in water because of the leveling effect. Does that ring a bell? The leveling effect. And so there's no driving force for this. I mean, HNO3 and HCl, same strength. You know, they're both going to yield 1 molar H plus, right? And so there should be no reaction here, but you can get a reaction. If instead you use silver chloride with hot concentrated nitric, then you'll be able to dissolve your silver chloride. Okay. Nitric is a special acid. Nitric and hydrochloric chemically are different because of their redox properties. Nitric has special redox properties, therefore we call them oxidizing acid, whereas HCl is your typical acid, and we call those mineral acids. And so here, there's some other products formed here. You could get brown fumes of NO and NO2. Actually, NO2. Here's another reaction. This is a reaction from Chem 1A, experiment 17. We take some lead-2 nitrate and some sodium hydroxide. We should precipitate out white lead-2 chloride and form some sodium nitrate. And so this is a double replacement. We get a precipitate here. Oops. This is wrong. Sorry. This shouldn't be lead-2 chloride. This should be lead-2 hydroxide. I made a mistake. I need to fix that. But if you add too much sodium hydroxide, the precipitate dissolves, and you're left with this. Now this is very weird because this is non-stoichiometric. For every lead-2, we need 2 hydroxides. Because we got a +2, we get 2 -1s, and that should neutralize. But this has 3 hydroxides for every Pb2+. Do you see that? And therefore, it's hard to see. This whole thing is going to have a net charge of -1. Do you know what this weird ion is called? This is called a complex ion, or coordination complex. And basically, we have too many hydroxides attaching onto the lead. And this stays as AQ. This dissolves in water. And so we might have predicted a precipitate of lead-2 hydroxide and not gotten it because too much sodium hydroxide, too concentrated. But nonetheless, you know, it's very powerful to be able to predict things, you know, keeping this basic assumption here. If we change things, then we need to figure out what's the new driving force. And that's what we're doing in Chem 1B. Because in Chem 1A, we did this qualitative, right? Kind of figure it out. Does a precipitate form? Yes? No. But in Chem 1B, we're going to see, you know, how strong is that driving force? We're going to put numbers on it. We're going to do it quantitatively. And so in Chem 1B, we're going to have some tools to handle this. Let's say we aren't dealing with 1 molar. Let's say we're dealing with 0.01 molar. Well, how's 0.01 molar going to change what we expect for the product? And so these are examples of equilibrium type calculations. the stoichiometry calculations that we're going to do, and those are going to involve determining the thermodynamic driving force. But the thermodynamic driving force isn't the only thing. You know, we're ignoring something here. And the thing that we're ignoring is the kinetics. And in Chem 1A, we haven't talked anything about the kinetics. In Chem 1B, we will talk about the kinetics. The kinetics is the speed of the reaction. And so, for example, we know that there's a driving force. Diamonds are unstable compared to graphite. And so diamonds should decompose into graphite. But are you going to be worried that your diamond is going to decompose into graphite? No. You know, because diamonds are, even though they're unstable relative to graphite, even though there should be a driving force, they're fairly what we call metastable. Metastable is, you know, the reaction is going to be so slow, nothing's going to be happening at all. And this is kinetics, and so we'll talk about kinetic barriers to reactions, even when we have a driving force, even when the product is more stable than the reactant. And so to get a full picture of this, then we need all these tools to help us predict, you know, chemical properties. But before we do that, we just want to get the basics down, and since everybody covers reactions differently, I want to make sure we're all on the same page. And so let me go through some of this. We'll take another break shortly. And so we're going to start off with metathesis reactions. Metathesis are, you know, ions. Looking for ions. So ions, where do you get ions? You get ions from ionic compounds. So typically we're either dealing with ions or we're dealing with ionic compounds. And our goal is to find the most favorable ion combination. Which ions like each other the most? And we know that based on if a precipitate forms, if a gas forms, if we're going from a stronger acid to weaker acid. Those are all clues that we're forming more stable products. And so we're going to be doing this qualitatively initially to figure it out. Not everything involves ions as well. Sometimes we deal with these weak electrolytes, molecular compounds, like ammonia and ammonia-like compounds. Ammonia, you know, is a weak base. Weak bases, what do they do in water? You know, weak bases are weak electrolytes. Weak electrolytes do what? Well, let's take a step back. There are two definitions of electrolytes. And so it depends. When you're talking about electrolyte and electrolyte properties, you have to know who you're talking to. So for example, if you're talking to a battery person, they're going to define electrolytes differently than, you know, somebody working on sports drinks. And so here, the definition that we're going to focus on is a strong electrolyte does what? Dissociates, right? 100% or close to it. Weak electrolytes do what? Partially dissociate. Right? Ammonia is a weak electrolyte, so does ammonia partially dissociate? No, ammonia does not partially dissociate. Ammonia does something else. Ammonia partially hydrolyzes water. And so hydrogen doesn't break off here. In other words, what happens with ammonia? Ammonia collides with the water molecule to form some ions. And those ions that are formed are ammonium and hydroxide. So this is called hydrolysis, reaction with water. We have a whole class of organic compounds that are like ammonia. So for example, if you take ammonia here and replace an H with a CH3 group, do you guys recall what a CH3 group is called? CH3? No, not methyl. If you take a hydrogen and replace it with a methyl group, a CH3, then rather than having a hydrogen bond to the nitrogen, we have a carbon bond to the nitrogen. Now, carbon and hydrogen have similar electronegativities, and so since they're very similar in terms of electronegativity, the electronic environment around nitrogen doesn't change much. And so we have a whole bunch of ammonia-like compounds like methylamine, dimethylamine, trimethylamine, ethylamine, propylamine, butylamine. All these amines that behave just like ammonia. And in other words, all these amines are weak electrolytes, weak bases, and these weak bases will weakly hydrolyze in water. They don't dissociate, because what ions would this dissociate into, right? And so they hydrolyze in water and to form a little bit of ammonium and hydroxide, or methyl ammonium and hydroxide, or dimethyl ammonium and hydroxide. And so these are called the amines, organic classical compounds. And these amines can react in metathesis reactions because we do form a small amount of ions, and those ions can undergo favorable combinations here. And so let me forward to the next slide, and then we'll take a break. Let's go ahead and take a break here, and then start up again at 4.